The algorithm that we just described works well for the fail-stop model, but it doesn't work for the fail-silent model since we used P, the perfect failure detector. So now let us look to a uniform broadcast algorithm in the fail-silent model where we have no access to failure detectors. So as I just said, we have been using perfect failure detectors. So the question is, these kind of failure detectors necessary for implementing a uniform reliable broadcast? The answer is no, as we will now provide an algorithm for uniform broadcast in the fail-silent model. And in this algorithm, we are going to use the ideas that we just mentioned in the beginning of this lecture, the idea of quorums. So let us remember idea of quorums. So quorums is a majority set. So we are going to assume a majority of correct processes in the system. So for example, a majority that is larger than half of the number of processes. So if we have 11 processes, the majority is 6. And if we have 12 processes, the majority is 7. And the most important idea of quorum that we are going to use is that in each quorum, there is always one correct process. That is the idea that we are going to use to implement our algorithm. So what is the algorithm then? The algorithm is actually more or less the same as the one we had before. So the basic idea is that every process eagerly best ever broadcast a message M when it receives the message M. And uniform deliver the message M when it receives M from a majority of processes. When it receives M from a majority of processes, it is safe to deliver the message M. So how we do that? We just use the same algorithm that we have just defined, the uniform eager reliable broadcast. But we just replace one single function. And this function is the can deliver definition. So can deliver condition now will be defined as we wait for an acknowledgement from a majority of processes for that specific message. So let us see now how we satisfy the properties of uniform reliable broadcast with this changed definition. So let's look to agreement. An agreement says if a process delivers, then all correct processes will uniformly deliver. So let's assume we have a process that uniform delivers. And what does it mean? It means it got an acknowledgement from a majority. But by the quorum property, in that majority, there is one process P that must be correct. And that process P must have done a best ever broadcast. So P will ensure that all correct processes will best ever deliver the message M because it did a best ever broadcast, and the best ever broadcast property, if a correct process best ever broadcast, all correct processes will deliver that message. Therefore, the correct processes, which are the majority, will ACK the message and uniformly deliver the message. So now let us look to validity. And validity says if the sender is correct, the sender will uniform deliver the message. So if a correct sender sends the message M, all correct nodes will best effort deliver M, which would mean that all correct nodes will best effort broadcast M, which means that the sender will receive a majority of acknowledgement, and therefore the sender will uniformly deliver M. So this is the correctness of the algorithm. Let us now look to an important concept, which is the concept of resilience. We mentioned it before, but let us now repeat it. What is resilience? It is the maximum number of faulty processes that an algorithm can tolerate or handle. In the fail-silent algorithm, with this majority ACK, the algorithm has a resilience less than half of the nodes in the system. So it means the algorithm works as long as no less than half of the nodes of the system fail. If more than that fail, the algorithm is stuck. In the fail-stop model, in fact, n-1 processes can fail and still the algorithm will work. So as you can see, there is no free lunch. With weaker assumptions in the model here, we will have also less resilience. So we are paying a price for being in the fail-silent model.